Now we are moving forward for the sponsor presentation. So for that, I would like to invite Paresh Patel sir one more time for the presentation. And the topic is GHZ Wireless Network for Smart Metering.
All right, so they're loading the presentation. I know there was supposed to be a coffee break right now, and I'm sure all of you are parched for some coffee to wake you up again. But I wanted to sort of go over all the issues. Can you hear me this way? Yeah? So it's kind of hard staying behind a mic. So I wanted to go and talk about sub-gigahertz. All right, you can hear me now, I guess. I wanted to talk about sub-gigahertz and the sub-gigahertz radios and what we're doing for the smart metering program here, because there's a lot of actually anxiety about that. The first thing, and the reason I wanted to talk about it is the first thing that I get asked many times is, what is the range, right? So there's a lot of chatter on the side. So what is the range of sub-gigahertz? That's the number one question I get asked all the time. So there's a lot of parameters that are involved with this. I'm going to step on this side. A lot of parameters are involved on this. And the first one, if you look at NB-IoT, and I'm just going to give you a quick spider graph. Now this spider graph is just not representative. The differences are very, very slight between all of these technologies, NB-IoT, LoRa, and Wi-Zen. These three technologies actually, NB-IoT uses a narrow band, but it uses a licensed spectrum. The LoRa and Wi-Zen are RF sub-gigahertz technologies that are in the unlicensed band. Now, each one of the spider graph, and I'll allude to all the different parameters that are each of the vertices that are there that actually make up that the overall functions that one needs to look at. Now, when you look at the spider graph, it looks like some things are so far apart and some things are close. Actually, but the real difference is minuscule, and I'll point those out as we go along. So area coverage. Between these three, one of the parameters that one needs to look at is area coverage. How easy it is or how far is this coverage going to be? And each one of those technologies have different mechanisms. For example, when you talk about range again, is that someone will say that NB-IoT has a 20-kilometer range. Someone will say that LoRa has a 25-kilometer range. And someone will say that Wi-Zen has a 5-kilometer range, right? So those are, and that affects the coverage. The next thing is infra deployment. Okay, so now what's interesting about NB-IoT is the tower's already ready, right? And so then the deployment of the nodes is very easy. However, for LoRa and Wi-Zen, you need a DCU that's installed somewhere. That deployment can be a bit difficult because now you have to add that not only to the node which is in the meter, but also the deployment of the actual DCU that's there and finding the appropriate locations. Conversely though, what happens when you're in a situation where the NB-IoT tower doesn't exist, right? Then the deployment for that is very expensive and may not be deployed. Whereas with the other two technologies, it's very easy to take a DCU and install it somewhere and deploy more. And then you have Wi-Zen, which is a meshed network as well, so you can hop from meter to extend your range as well. So these are some of the infra deployment types of stuff. And then overall cost efficiency also looked at, right? We Indians love to make sure that we get the most value for our money, right? And so what technologies are going to give us the best bang for our buck is what we're going to look at. And each one of these has different nuances that are there. For example, when you're doing sub-gigahertz, the cost can be very minuscule or very big, depending on how you decide to deploy these things. One example is if you take a LoRa radio RF module and you take a Wi-Zen RF module, basically the chips on there are pretty much equal in price parity wise. But then when you look at the rest of the infrastructure for on board, making sure that do you put an RF balun? Do you put some other mechanisms in there to increase your transmit power and also increase your receive sensitivity, which makes or breaks whether something works or not. So those are the types of things that we have to look at. So cost should be a factor, but it shouldn't be the overriding factor. Battery life. In this particular case, let's say if we're talking about metering general, we're talking about electricity meter directly right now, but there's also gas metering and there's also water metering, right? And so those are the same level of amount of units that need to be deployed. So the battery life for gas and water is very important because you don't have electricity next to anything. So that's where the technology will change. You may want to use a LoRa technology versus an NB-IoT technology or versus a Wizen technology. Then the quality of service. So for example, when you have NB-IoT, you're going to get a guaranteed SLA from your communication service provider. They're going to basically guarantee that quality for you. And a tower is not going to go down so easily, right? Whereas when you look at LoRa or Wizen, if someone turns off a switch to the gateway, and this has happened to some of our deployments, all of a sudden you start losing readings from something. So, you know, the quality of service in one place it's managed from a central location, and another service it's decentralized. So, but with some body overseeing that. So that you can have quality of service issues when you're deploying various different technologies. And by the way, I'm not saying any one of these technologies is better than the other. And as I alluded to in the panel session, is that all of them can be used. All of them should be used because you'll have different use cases for each. Packet size. This is a key important one because the packet size that you need to transmit is going to really dictate what technology you're going to use. For example, LoRa packet size is 244 bytes or 245 bytes per packet. Now, in electricity metering, I know this is getting a little bit too technical, but in electricity metering, you use DLMS messages, and those messages can be 350 bytes or larger. So then now you have to packetize and chunk things up and LoRa, and then as you start using more packets, the more radio airwaves you decide to occupy. So therefore, you know, LoRa for electricity meters is not heard of, but for gas and water, it's perfect. Very low power, battery life lasts long, everything is good. Wizen has a good story from a packet size, and of course NB-IoT has the best in terms of packet size. But there are trade-offs again for that one. Latency performance. So that means that how long is it going to take your message once it's received to get out from a radio perspective? And this is like radio management type stuff. So each one has a varying perspective on radios as well. Scalability. So again, this all leads to kind of all the other things you've seen down there is scalability. How do you scale these things? What's the easiest technology that's going to scale? And you have to take into all these factors as well. And then security. So, okay, so now what offers the best security? We alluded to security. In the UK, we've gone through some products that we've built for the UK with MI6 level security. So that means that the same ministry that authored license to kill also licenses us to put stuff for national infrastructure. And just the certification in the UK to get onto the smart metering network costs a minimum of 150,000 pounds. In India, that's not going to fly, right? And so what we need to, but it's a pressing issue. So security, which technology is going to offer security? And the nice thing is all three of them, we can offer levels of security, but they have to be basically thought through and then implemented. And then the last thing that I really wanted to talk about was range. Like I said, all of the above contribute to range, right? And the range is going to dictate how many meters that you're going to install. For example, let's say we talk about GPRS or NB-IoT. There are effects that when it rains, when there's cloud cover and stuff like that, you lose signal. Or there's so much chatter, the airwaves are so congested that you don't get a signal out. These are the things that actually cause real problems in the metering network. So the range is a combination of a number of factors. And then what everybody needs to understand is when someone says the range is 20 kilometers, there's an up to on everything, right? If you have walls, if you have trees, if you have rain, all of that gets affected. All of that gets affected. And so the thing is that, this is a little bit technical, but I wanted to show this thing. So there is, ideally, the Indian manufacturers for radio communication should, they can transmit at 23 dB, which is about 500 milliwatts of power, and they can do at 1% duty cycle. So that means in, let's say, 1 hour, 1%, 60 minutes, 1% of that hour is 6 minutes. So you have maximum of 6 minutes to transmit all your packets together to make sure you fall in line with international standards on radio communication at 865 to 867 megahertz. And so that means you have different topologies. You can transmit at various intervals. You can transmit all in one packet. But if I'm transmitting, because I'm transmitting, I'm shouting the loudest as a node. And I'm transmitting for that 6 minutes fully. Then what happens is that when you transmit for that, then nobody else gets seen for 6 minutes. So that cannot happen. So that network management needs to be looked at very carefully. And that also affects the range as well. Because people think, oh, range is not good. But the issue is not the range. The range is not good because someone isn't able to talk to the thing. If you're whispering, like right now I'm shouting, that way you guys can hear me over the chatter in the background, right? The signal to noise ratio is more. But the idea is that the same thing here in radio technology, that needs to be balanced and that affects the range. Then this is fading effects. So, from physics point of view, as you go further distance away, your output, your power decreases that's available to you. The closer you are to a transmitter, the more signal you get, the further you are for a transmitter, the less signal you get. On top of that, you have things like fading effects. So the trees, the rain, how it bounces off the ground, how your antenna is positioned, all of that matters in fading effects. And that's why the installation is very key. Okay? So if you don't have trained manpower for basically properly installing everything, then you will not get good coverage of the network. So if you don't get good coverage, what's the solution for GPRS NB-IoT? Maybe the solution is, another tower, but there's a cost associated with it, then that can't be done. However, if it's a LoRa or Wizen, then you have to put another gateway that's there. But again, there's a cost associated with it. So all of these things need to be looked at the very beginning. And what needs to happen is that when an implementation is planned, some RF surveys need to be done in advance so that you know where and how to deploy the cellular companies do this when they're putting a new tower. They do an RF survey, but when you're using sub-gigahertz, you have to also do an RF survey to figure out what the optimal location is for a gateway. Otherwise, you're going to put gateways in the wrong place, and then now to cover that, you have to put additional gateways. So that again is a cost issue that's there. So, and then when you get down to the nitty-gritty, there's this small little module about this size inside of every meter, or both for NB-IoT or Wizen or 6-LoWPAN or Zigbee or whatever RF technology that wants to be used. Very small little thing. And how that's designed actually makes a difference. But see, in India, people come to me and say, we should get the module for 300 rupees. I said, great. Now, do you want it to work? Right? And the real cost is about 680 to 700 rupees. And that's when you add all the RF components like balloons and switchers and stuff like that to make sure your signal loss path from the chip all the way to the antenna is not lost. Does everybody know what 3 dB means in the world of RF? 3 dB means if you say that you're losing 3 dB, that means half your power is lost. That means half your distance is lost. Now, in the UK, we had lots of fights with Telefonica and Toshiba because the Toshiba guys said that the antenna they wanted to put out inside of their sub-gigahertz NAN radio was in this position. Telefonica said, no, 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 it should be in this position. Now, why? And there was a huge argument. I was brought in to actually mediate, okay? And the ultimate conclusion was that it has to be in this position because the network antennas are in this position. If you have one antenna like this and another antenna like this, there's a 3 to 6 dB loss. This the installers need to know. Because when I see the installations over here for various things, the antenna is in any position. So anyways, those are the factors that I want to talk about, and I've taken over my time because Foram, who's actually been in ground in India installing various RF technologies, is going to talk about some of the other groundwork that there. So I talked kind of about the theory. Now you're going to get the real scoop on what happens.
For giving like a detailed overview or you can say the theory part of the RF technology and how this technology is like how and the main crux of the overall deployment is the range, how you achieve the range. So we done some of the field studies and cover up or performed based on the different deployment environment like the indoor environment, the street environment or the open field. And cover up prepared some of the graphs. Yeah. So here you can see we just captured the RSSI based on the RF communication, and here you can see in the indoor environment. Yeah. So yeah, as you can see, if it's an indoor environment, then the complete RSSI loss happens within the 50 meters of the range. While with the street environment, it drastically drops initially because of the nearby buildings and the nearby other field environments. But then it stabilizes and reaches up to the 300 meters. While in the open field environment, it does not drastically drop because it's a complete open field, but it gradually, because of the RF signal, tend to reduce its capacity, so it eventually gets reduced and it reaches up to the 300 meters. Again, we captured the packet loss against that, and if you see in the indoor environment up to 30 meters, you don't see any kind of packet losses, just because the RSSI is healthy, link quality is healthy in that sense. But then you start to see the packet losses, and up to within the 50 meter, you see the 10% of the packet losses in the indoor environment, while in the street environment or the open field, you see the 150 meter range is healthy, where you don't see any kind of losses, any kind of packet losses. While you start seeing the packet losses after 150 meter, where RSI starts dropping below 70 dBm. Another factor is the transmit power. As like Paresh mentioned, there are a lot of other factors which covers the range. Another factor is the transmit power, and if you start with the lower transmit power, your signal will reach up to like 200 meters. If you increase your transmit power, your signal tend to reach more distance, but it goes maximum of the 300 meters. Now, very important parameter what Paresh has mentioned, this is the interference which is happening due to rain, probably due to other rogue device communicating due to GSM communication, right? So we captured the noise floor at the open field, and if you see, there is it's a flat line at the 90 dBm, where all your signals all your receivers can listen up to the 90 dBm whatever transmitter is transmitting. Below 90 dBm, receiver starts seeing the issues because of the it cannot differentiate between the actual communication signal and the noise. While because of some rogue device in the other region, you can see you are always getting a minus 70 dBm the noise. So in that scenario where your receiver will face the difficulties, because after 70 dBm of the actual signal, it will start facing the issues understanding the actual signals. So eventually it will decrease your communication rate, as you see here up to 75, up to minus 80 dBm. You are able to listen the signals because of the minus 90 dBm noise level. But if your noise level reach up to the minus 70, then you will start, like your receiver will start facing difficulties. After minus 70, your packet loss it will start increasing. So your range will be from 50 or from 300, your range will be limited to 200 or 30 meters. I'm going wrong way. Yeah. So these are some of the site survey we have done and prepared the graph overall your signal propagation, and you can see the green area, the center green area is where your devices can maintain the healthy link. You can consider it as in your healthy link, and two devices can communicate without any issue within the green area. Once you start going towards the blue area, your external environment will affect your communication signals. So you can start seeing intermittent issues. You see like it is communicating for some time, and during rain you start losing your packets. Yeah, and these are the real tests performed at one of the site where the simulation parameter shows your range should be like this much distance can be covered within the 72 dBm, minus 72 dBm, while the real test shows that it still happens like it reaches like minus 75 or minus 80 dBm. So simulation, apart from the simulation is not the covering the actual things. And because of the environment, because of the nearby buildings, trees, and all those factors happens, and your signal starts to degrade more than the simulation. Yeah, so based on the RF survey, we covered so this is the real deployment what we have performed on field, and prepared a map, mapped all the devices required, and created a boundary where DCU needs to be placed. Once DCUs are placed, DCU coverage is, you can see within this red area, but there are still few devices which are outside the red area, which are not covered by the DCU. You can always put another DCU to cover those devices, but eventually that will increase the cost. So here what we have done is we prepared the heterogeneous network where the DCUs covers the entire red side, and couple of devices which are not inside the DCU coverage are converted to the GSM. And yeah, so these are few glimpses of the network management software for the Bison, and you can see like how the topologies are created, how many nodes are connected, and how DCUs are online, which are the offline nodes, non-communicating nodes. You can see the node parameters. You can see all the router or the DCU parameters, and the hidden system. Here you can see that the entire network is prepared, and some of the devices are like 25,000 meters are there around. Some of the devices, most of the devices are on the RF. Some of the devices are on the GSM, covers the entire communications, prepared the entire infrastructure, and how the communication happening between all those devices. Eventually, the HES side, it doesn't matter whether it's on the RFs, whether it's on the LoRa or it's on the GSM. HES understands all the packets because it's just a DLMS packet. HES captures all the metering data and put those details and provide all the interfaces. Yeah.
So thank you, Forum. And for that, we have about a minute and a half. Does the audience have any questions for us? Yeah. The gentleman up there.
Hi, my name is Ramakrishna. So very wonderfully you put it in the sub-gigahertz one. That includes the survey. So what are your recommendations or best practices that you would like to give? Or how do you go about?
There are many recommendations, but I guess the first one is to start off with a proper module from a proper vendor, because for the electricity and gas and water. Main thing is people think that if you just get a module, that you integrate it into the meter, then it's going to work nicely. But the problem is it doesn't, because actually as soon as you put the module inside the meter, that causes the antenna interference and the radio patterns to change within the meter, and so your antenna sometimes becomes ineffective. So that's the first and foremost one, and then it's the matter of understanding your own technology. Right? Is that what is the range? Best thing for do that understanding is to do an RF survey.
RF survey, yeah.
Yes. So I was about to talk about that because before the project implementation, normally we go about doing this survey or the RSSI, the radar, whatever you have shown with regards to that. But now the complexity being with regards to the kind of technology that they have come into that, whether LoRa or NB-IoT or these. So what is your suggestion, or you have earlier said that you don't have anything against anybody, but still from your technological prowess that you have, what is it that you suggest?
So yeah, like I said, I don't actually. We have modules that cover all the technologies. So actually, I don't have any problems with any of them. It just whatever the manufacturer or whatever the installer, whoever the customer is that wants to install it, they have to take a look at the overall cost and manage the cost between, do I use a GPRS solution, do I use an NB-IoT solution? I mean, NB-IoT isn't available really in India, so not yet anyways. It's in pilot in not many places.
As we speak, I think a couple of days ago, I think Ubix has gone ahead with
That's
the
right.
NB-IoT rollout for massively.
Exactly. Yeah.
Yeah.
But yeah. So it's happening, is what
It's
I'm saying.
happening.
But it didn't happen, 2-3 months ago. So, but that's happening, and then you can definitely, if the cost factor is absorbable from an NB-IoT perspective, use NB-IoT. If the cost factor for sub-gigahertz is correct, use sub-gigahertz. And it depends on your topology. There may be some cases where there's no NB-IoT tower, so you have to use sub-gigahertz.
So then you suggest for a private 5G?
Private 5G is fine too. As long as the small cells are available to actually make that happen, then it's fine. Again, cost factor comes into picture as well. Yeah. All right. Our time is okay. Since as a moderator I didn't get a chance to answer, I'll have one question from the gentleman up in front.
Yeah, I'm Managing Director of Chescom, Chamundeshwari Electric Supply Company. It's a distribution company in Karnataka. I cover 5 districts of distribution. In that 2 districts, they are covered with the mountains and terrains. So I'm basically a radio communication man. Fine? So this radio communication is going to play a vital role in the effectiveness of the smart metering system. Though of course in the urban area there may be disturbances, but still you can cover up by adopting additional equipments, etc. How are we really going to, you see, if you look at Haryana, Punjab, where there is a plain area, there is going to be no problem, you can cover as you say. But where it's not a plain area but a rural area, and it's really going to be a challenge. And the cost effectiveness when we see, though of course we say in a thumb rule that it is going to cost this much, this much, this much, but in some utility where 50% of the utility is covered by mountain terrains, hills, etc. And the per capita consumption, if you see per month, is less than 20 units or 30 units in such areas. Is it really going to be viable? And how effectiveness, cost effectiveness is going to be to make it viable in such areas?
So it's a good question, and the frank answer is it's not cost effective.
Huh?
It's not going to be
At all
cost
cost
effective.
effective.
That's correct,
So
yeah.
there's one technology that may be okay for this, and that is power line communication, right? So we're going to use the existing power line infrastructure that if you look at LawnWorks or you look at G3 PLC, over the power line you can communicate. If there's no transformer in the mix, then you could actually communicate 2 to 3 kilometers that way, and you can actually do the
No,
thing.
my feeder runs into 70 to 80 kilometer per feeder.
Yes, but if there's no,
It is there.
if there's no transformer
is
within the
there.
feeder,
It
then there's
is.
an opportunity to create
No, it is,
localized.
transformers are there because in that feeder we have to, give the power to all those who are in need in the entire feeder.
Yes.
It is not a fag end where the transformer is there.
So
You
again,
have to cover everybody.
The direct answer to your question is it's a very difficult problem, as you've stated, unless you're using a satellite which basically then looks down upon the entire area. That's not feasible as well, right?
It is
Then you
like
have to
this.
put exactly. Then you have to put multiple gateways
Yeah.
and DCUs to do this. That's a cost issue.
Yeah.
So there's someone will have to bear it. Maybe the consumer will bear it. I don't know, but.
No. All that what is now being discussed over here, I understand that tomorrow consumer is going to pay. But the government regulation, we must understand that the smart metering, we cannot put single NP cost on the consumer. It shall be borne by discoms only. The cost of implementation is not on the capex mode. If it is on the capex, we can put it on the billing for the consumers later on. If it is not on the capex, it is already a meter which is installed. No, customers are not going to pay.
Yes, so someone, but my point is that someone is going to absorb that if it's there. So that's anyways.
Of course, now the technicality I have understood, we'll try to elicit some more information in other sessions.
Yeah, no issues. Thank you very much, everybody. Thank you.
Thank you.